Hi everyone, and my name is Udi. Today we're going to talk about ClickHouse and some of what we've learned from a few years of using it. ClickHouse keeps on getting more and more popular, more and more traction. This talk is addressed mostly to those who are curious about ClickHouse and consider using it or just getting started. So a bit about me. I'm Udi. I'm the chief architect at GroundCover. GroundCover is an observability platform deployed in a bring your own cloud deployment model. And as such, we need to manage a lot of analytical data collected through our platform. And ClickHouse is a main part of how we do it. So today I'll share some fundamentals that, in my opinion, are critical to make the most out of ClickHouse. So we'll start with the foundations, with what is ClickHouse and when it is a good decision to use it. We'll continue with some main aspects of ClickHouse architecture. It's columnar storage, it's support for distributed deployment, and we'll talk a bit about the merge tree table engine. Then we'll cover some topics that we think are some practical lessons for each user starting to use ClickHouse. So let's start with what actually is ClickHouse. So ClickHouse is an open source OLAP columnar distributed database. Let's break these four terms down. ClickHouse is open source. It was created initially internally at Yandex, but it is now released in Apache 2.0 license. It is actively and very rapidly developed, and its code is available on GitHub. It's run by an independent company called, surprisingly, ClickHouse, which offers also managed cloud deployments of ClickHouse called ClickHouse Cloud. OLAP means online analytical processing, and ClickHouse is built for fast ingestion and querying over large data sets, and it favors speed and scale over capabilities like transactional capabilities, which more traditional databases, which are OLTP database, offer and focus on. And ClickHouse is columnar. This means data stored by ClickHouse is stored on disk by columns and not by rows, and we'll dive a bit into it in the next slides. And last, ClickHouse is built for distributed deployment. It is horizontally and vertically scalable, which is important for managing on cloud environments and for scaling with increasing and dynamic volumes of the data and usage. The next question you should ask yourself is ClickHouse right for me? And this is determined from the properties we've just discussed. ClickHouse is good for analytical purposes with high cardinality dimension and append mostly usage patterns where you don't need to frequently update or delete rows, and you don't require transactional consistency. It also supports, but doesn't excel, with join-heavy queries, where you need to merge data from different tables or different subqueries during the query time. If you need both these sets of capabilities, it really might be a good idea to use another OLTP database like Postgres along ClickHouse and use them both, each for what it's good at. Just remember, every database has its own limitations. Now continue with some aspects of ClickHouse architecture. I think this is where stuff begins to get really interesting. We mentioned earlier that ClickHouse is columnar. What does it mean and why does it matter? In row-based databases, data is stored row by row. It will be in files where the whole row is stored, followed by the next row. It's very useful and convenient when you want to fetch the whole row. Everything is in the same place. In columnar databases, each column is stored separately in its own stream of file. For example, in this photo, we have the temp column. So in columnar databases, it will be stored in its own file, starting with the value 14, then the value 13. The wind speed column will be stored in a different file, starting with 21, then 9. This approach isn't very intuitive, but it's actually very strong. Why so? First, you only read the columns you need. If you have select queries that select only some of the columns of the table, When you query it over a columnar database, it will need to fetch only the columns you asked for. And it will just keep, and it won't touch the relevant data. Second is that you get much better compression, because similar data is stored together. And better compression means not only you need less storage, but you also need to read less data from the disk, which can be a major bottleneck, the disk throughput, in a lot of storage solutions. ClickHouse also has a variety of codecs and compression algorithms, so it's very versatile. For any data type you use, it can compress it very efficiently. And third, this model allows very simple and effective distribution of the data for parallel processing, which ClickHouse is really good at. And this really leads us to the next topic of scaling ClickHouse. ClickHouse supports both sharding and replication. Sharding means distributing the data across different nodes. We use this when we need to extend our deployment resources over what we can on a single machine or a single disk. Replications means copying the data of each shard to another server. We use this for high availability and resilience, so that when a single replica is either temporarily unavailable or forever corrupted, there is still at least one copy of the data still available. ClickHouse has a native support for both of these capabilities, with the distributed table engine and the replicated merge tree table engine. And the way we do it in ClickHouse is we define a ClickHouse cluster. For example, this cluster has 3 different shards, 2 replicas each. And we define the tables we want to replicate as replicated table. And we need to write only once to those tables, and ClickHouse will handle the replication. It will copy the needed data to the other replica. And we can also define a distributed table over those regular local tables. And using the distributed table, we can have one interface for all those tables across all shards. You can query the distributed table and get the results combined, merged from all of the shards together. And you can insert data to the distributed table, and it will spread it across the shards, one row for each shard. Our next topic is the merge tree engine. This is the heart of ClickHouse. This is what's powering the tables inside ClickHouse. It's a very complicated topic. You don't need to understand it to bits, but gaining a brief understanding of its structure, is very useful for debugging and for optimizing your ClickHouse system. So merge tree is built of immutable data parts with the surprising name of parts, and every write is flushed to disk as a new part. ClickHouse in the background automatically and frequently merges existing small parts into bigger parts. Each part is sorted according to the order by key defined in the table schema. And there's a sparse primary index leveraging this order when filtering by this key. So the primary index helps ClickHouse to understand very quickly which parts of this table it needs to read to fetch from the disk and start scanning, and also inside those parts where to look at. So this is why the order in key is a very critical design decision. It affects both the compression ratio, because it affects the order of the rows, and also it affects the primary index usage. So the order in key needs to balance between these two. It needs to organize the rows such that similar data is stored together so that compression will be as efficient as possible. But it also should consist of keys you normally filter on, so the primary index will get into effect. If you don't use the primary key, the ordering key, as a filter, then the primary index won't come into effect, and you'll probably end up scanning the whole table. There are also secondary indexes, but we won't get into it today. The merges performed by ClickHouse in the background of small parts to bigger parts are also opportunities to do some aggregations on the merged data. You can define the aggregation as part of the merge tree table, and ClickHouse will apply it when it merges and see two or more rows with the same ordering key. For example, you can use it to resolve duplication issues, to dedupe, or to maintain the last state of some entity. ClickHouse has these sets of flavors of merged tree tables, so it allows a lot of different aggregation mechanisms. We'll see an example in the next slide. Note that these aggregations, they happen during the merges, so their timing is not guaranteed. If you are querying the table and you want to make sure you only get the aggregated results, you can use the final keyword, and then it will apply it on read. Now we'll move on to some lessons we've learned along the way that I think are worth mentioning. The first one is batch on writes. So we've mentioned earlier that every write is flushed to disk as a new part. When you create parts faster than ClickHouse is able to merge them, you will start seeing errors, this too many parts error. This is a very common scenario for a lot of new ClickHouse users. To make ClickHouse life easier, it's a very good practice to batch those writes as part of the writers and make each batch as large as possible. As few writes as possible, as large as possible. You can achieve this either by adapting the components you use to write to ClickHouse, or by adding a new layer, a service that will take care of the writes to ClickHouse, and it will handle the batching. Also, you can check out some more advanced options like the object storage queue, which is kind of a simple Kafka alternative based on S3 or other object storage solutions. And also the settings that allow asynchronous inserts that basically move the responsibility of batching to ClickHouse itself. Next lesson, we've mentioned that ClickHouse doesn't excel with joins and with updates. You can design your data model to avoid this operation as much as possible. For example, one method to avoid join is denormalization of the data. The idea here is adding the data that is usually needed when querying as part of each row, even if it is redundant and duplicate. Take, for example, an event. We have an events table, and each event is associated with an entity. And we have this other table of entities with metadata for each entity. Normally, when you query an event, you also want the metadata of the entity associated with it. So denormalization will be taking the metadata of the entity and put it as part of the event, as part of the row of the event in the events table, even if it means duplicating the data and storing it much more times than actually needed. This is, of course, more wasteful in storage, but it allows much, much faster queries because ClickHouse doesn't need to go to other tables and find the relevant row in them. And also the columnar characteristic of ClickHouse, which I mentioned earlier, is really effective on making this excessive data compressed very well. So it might be not a very excessive storage issue. This is for joins. And for updates, you can adjust your data model to be based on appends with some version or a timestamp, the simplest option, and have a native aggregation like the replacing merge tree as part of the table. Then ClickHouse will handle on its own the mutation in the background, and eventually it will store only one final state for this key, without you having to schedule these mutations and without affecting the inserts, making the inserts slow. Next one is pre-aggregate. ClickHouse has a very powerful capability called materialized views. Materialized views is a common term in databases, but it doesn't always mean the same thing. In ClickHouse, a materialized view is a write that is triggered on inserted data. If you have complex but frequent queries, you can use materialized views to make pre-calculation for these common hard queries. For example, let's say we have this events table of raw events, and we frequently need to know how many events were for each event type. This table can go, for example, like years backwards. It can be a very, very large table. So we can create an aggregative table, event summary, for example, which uses the summing merge tree engine. This table will sum the count of each event type inserted to it. And we can create a materialized view defined like this, which will populate the aggregative table. So what happens when a new insert is done? When a new insert is done, this query defining the materialized view of a select event type count as count from events row group by event type will be run on the new data, only the new data, the latest batch, and its result will be written to the aggregative table. Then the sum and merge tree will come into action, merges everything, so that each event type has one final count, so we can very quickly get our summary of how many events were for each event type. The trade-off here is, of course, the additional storage being used and some additional resources being used on the right path. So it's really up to your use case, but if you have those use cases of complex frequent queries, it can make them very fast from impossible if every user had to count on all this historical data every time all over again. And the last part, the last lesson, is how to monitor ClickHouse. ClickHouse is a very complex system, and understanding what's going on inside it is not very trivial. There are a lot of tools baked natively into ClickHouse to help you monitor it. The first thing is its logs, the ClickHouse server logs. ClickHouse outputs a lot of logs, and they can shed a lot of light over what's going on internally. Specifically, it's very convenient to track those logs for errors and seeing what causes them. Next is the Prometheus metrics exposed by ClickHouse, which help observing the general state of the server, things like amount of ingested data, rate of queries, average query latency, etc. But the most advanced tool is the system table. There are lots of system tables in the system database, and basically the entire ClickHouse full state can be observed using those tables. Specifically, the query log system is very important and very helpful when you want to query specific queries. You can get very, very detailed information about every single query when in the ClickHouse server, a very detailed profile of how many bytes it weighed, how much time it took, how many rows it had to scan, gaining a very deep understanding. It's very important for troubleshooting long queries and optimizing them. So to conclude, we discussed about ClickHouse and its properties. We saw it's very powerful, but has some limitations. And we spoke about some core architectural elements of ClickHouse and the importance of designing your table schemas according to those elements. And we finished with some principles that are different, might be different from the usual patterns you might know from traditional other databases, but are very suitable for ClickHouse, for making the ClickHouse experience better. So thank you.